Conference 2026. And thank you for joining us this morning. This is the System of Systems Adapting Lessons from Other Industries for AECO. If you were looking for the functional recovery focused data collection session, that is upstairs in the ballroom. Otherwise, thank you for joining with us today. Today we have two speakers, Joe Manganelli and Amir Golalipour. Sorry.
You got it.
And to also note, it took me a really long time to learn my husband's name, so I'm really proud of myself. And with that said, at this point, I'd like to ask Amir if you wouldn't mind doing a few minutes to introduce yourself, and then we'll have Joe introduce himself.
Sure. Good morning, everyone. My name is Amir Golalipour. I'm with U.S. Department of Transportation, Federal Highway Administration. I've been in different programs with Federal Highway for the past 14 years. Now I manage infrastructure resilience and safety program for the past 6 years. In that program, we mainly focusing on how we are looking at multi-hazard, multi-asset type of framework. And we are hoping to discuss some of that today with you, that how that could relate back to the building science. And my background education-wise, I'm a civil engineer, bachelor all the way to the PhD, and I've been focusing mostly on transportation infrastructure. But during my master and bachelor, I have done work on vertical construction, so I have a little bit background in concrete and still basically construction. Thank you.
Joe?
Hi, my name is Joe Manganelli. I have three roles, I guess, formal roles. I'm a principal architect at a company called Floor. We design and build factories. I've worked on biotech, pharma, food processing, mining and metals, consumer goods, production plants, and before that I did a lot of school and higher ed work. Second, I have my own, so I have a dual background, architecture and human factors. Architecture, I think you all are familiar with. Human factors generally entails three things: ergonomics, which most people understand and know. Then there's what user experience research and design, like how to make websites and software more user-friendly. And then there's like a mission-critical UX where you do the same thing, but like say for a control room, for a power plant or something, where you use more scientific methods to make sure that the way it operates is reducing errors and usable for the operators. So I have a background in human factors, and I have a side consultancy, Explore Design LLC, that focuses on human factors work. What's happened, interestingly, with the human factors work is where I found most opportunity the last few years, or several years, is projects developing or trying to manage AI systems. So my contribution to this panel will be more focused on automation and AI systems from a human factors perspective. And then this has also led me to be an adjunct professor in the School of Information at Kent State University. Leading into that, I had done a postdoc studying distracted driving about 10 or 15 years ago. So as far as the applications where the work is focused with automated systems and AI, it's mostly healthcare, autonomous vehicles, but I've been bringing methods from systems engineering and human factors into architectural practice for a while now.
Great. And I am Michelle Mihalik. I am the Senior Director of Provisions and Standards here at NIBS. And with that said, I will be your moderator today. We will have a microphone for any questions or discussion points. So if you are interested in making a comment or having questions, please raise your hand, and we'll have the microphone brought up to you, because this is also being live streamed. Also, if you wouldn't mind silencing your phones, it would be greatly appreciated. And with that said, Amir, and we'll hand this over to you.
Thank you. Since it's so hard for me just to stay in one place, I'm going to walk around if that's okay with everyone. As you can see from the slides, I'm going to talk about what we have been doing in federal highway and US DOT in terms of resilient. And I typically like to engage audience, so I ask questions, and if I don't get a response, I'm going to volunteer you to provide a response, so be ready for that. So this is what I should show you. This is what our lawyers ask us to. So the summary of that is that you can ignore whatever I say because the U.S. government does not, endorse, and then what we are saying here is not related to a statutory requirement. So yesterday, actually, yesterday morning when I was talking to a couple of folks here, they're talking that, yeah, we haven't established even what resilience means. And with show of hand, how many of you know a definition for the resilience that is being set by an agency or your organization? Just show of hand. Okay, 1, 2, 3, 4, 5. Okay, so a handful of people. So as I can see, the majority of room, on the resilience definition, even we don't have an agreement or we haven't set type of a definition. So this is a definition that U.S. Department of Transportation has been using, and it is, as you can see in those links. I don't know if I can. No, it doesn't have it. But if you look at those, there are links into the congressional statutory requirements that we have. But if I want to summarize that, resilience, it goes back to two parts. One part of it is about the planning, adaptation, and basically preparation of the for any type of hazard or extreme events. The second part of that is about response and recovery. So to make it easier is that if I want to explain it very simple, resilience is nothing rather than risk management, how we are going to manage our risks. And what is risk? At least in infrastructure and transportation, we are looking at 3 different elements for risk. I actually have the notes because I know that I keep forgetting some of those. So one part of that is impact. So in terms of the building science, if a hailstorm happens, what is going to be the impact on your building, basically, right? So that's the first one, is impact. The impact, we need to understand what would be the impact. The second part of it is a probability. In building science, you guys walk into earthquake. What is the probability of an 8 basically magnitude earthquake versus 7 versus 6? So that's the probability. And the last one is a vulnerability. And that's very important for us in this group to discuss that. What is our vulnerability of our system? And it is a system of systems. So we need to understand where our choke points are, where some of our critical points are for our buildings or for our assets, and then how those could be impacted. So basically, resilience would be, you get your risk and you look at the criticality, risk goes and criticality goes up, resilience comes down, and vice versa. If you bring your risks down, your resilience goes up. And in terms of resilience, we use a concept that has been used internationally. They call it 4 Rs. So robustness, rapidity, redundancy, and resourcefulness. With these 4 Rs principles, you are making sure that your system can withstand some of those, and also if there are some impacts, you can recover rapidly.
Excuse me.
Sure.
Those 4 Rs again? Or?
Sure. Robustness, rapidity, because you need to rapidly recover, redundancy, and a resourcefulness. Like redundancy, I don't know about the building, but in infrastructure is very important. For those, how many of you are living in DC metropolitan area? Okay, good, a lot of you. It was about a month ago that you guys remember there was a rainstorm. It wasn't a crazy one, it was about an hour and a half or 2 hours, but it created a gridlock in the whole DMV. Just one rain event. It was not a crazy storm, but it was because of the intensity in a short period. We had basically some partial flooding in different places, 495, 395, 66, Georgetown Parkway, all of that, they were basically gridlocked. And people, they were stranded like on the road for 2-3 hours. So redundancy is important, because if right now, for those that are living here, what is the most choke point in our DMV area? American Legion Bridge. Whenever that bridge, something happens to it, the whole area is impacted. It was, I think, right before the pandemic, if you guys remember, there was a big fuel truck that overturned on that bridge. A lot of my colleagues that day, they were in DC. I left that day early. They couldn't get home in Maryland. So they had to stay in DC the whole night. And imagine, this is our nation's capital, and one truck can cause such a. So redundancy, resilience is very important. I want to speed up a little bit. So, and this is again goes back to our statutory requirement. A lot of times people, they look into this in terms of cost or how they're looking at. For us, is a statutory requirement. As asset management plans, we need to look at resilience. We need to have these risk-based plans in place. And why is that important? Because we have these emergency events. I don't know if you're just following news. Every year we have these $1 billion events happening in the US. And unfortunately, for the past 10 years, every year, the number of those $1 billion events are keep increasing. So when we have these repeated emergency events, we need to think about how we can basically reduce the impact. We cannot do same old, because what happens is going to fail, and then you need to pay again and again. So we need to find a way that for, at least for us and roads, highways, and bridges, we need to make sure that we can find a solution for it. And a lot of you guys know that when this type of big event happen, where federal highway and US DOT comes into place, is with ER program, emergency relief, so we pay to the states. As you guys remember, Helene happened just recently. So can you guys guess how much Helene impacted in terms of dollars just the transportation assets? Just give me numbers. $3.5 billion, okay. What? How much?
10 billion.
Okay.
Did you say the average?
I know the total of the impact of the Helene on transportation assets only. I'm not talking about the user costs, I'm not talking about the homes, I'm just talking about assets. It was more than $5 billion. Just one event, less than a week, cost us $5 billion just for roads and highways. We don't have that much money in our nation right now. We are in deficit. So that's why it's important that how we are spending some of this ER money. And just to put it in perspective, again, you guys know that for your buildings, but in our transportation assets, we did a studies to say that what's the impact of the environmental factors. We are not looking at traffic, we are not looking at accidents. Just if I build this bridge or road, and I just leave it there for 10, 20 years, how much would be the damage? So for like the flexible pavements or those black roadways, is more than 1/3 of that just coming from the environmental factors. And this is not including extreme events. So if you have a major hurricane or wildfire, that even goes up. So those are huge numbers that we are dealing with. These are some of the studies that we have done. I just put it here in case you guys like to see some of the way that we are doing it. There are links here too. This is for flooding on roadways, and this is for wildfire. I just want to focus a little bit on this one because this was the first nationally study on wildfire, and you're looking at it, and when you're looking at the impacts of it is much more than we understand, because some part of these impacts are kind of what we call it indirect impacts. And again, I'll get to that when we are doing more discussion. And throughout yesterday and this morning, we have been talking about innovation. Innovation, what does innovation even mean and how we are getting to it? So we did recently a study to look at what type of innovative technology or practices we can bring it to building resilience for our assets. And as part of that, we talked to the State Department of Transportation, local agencies, MPOs, counties, And this is one part of it. One of them goes back to the whole concept of asset management, and you guys are really good in it. We need to bring this risk-based methodology to our asset management to understand how we can balance the risk and the cost. And then design and standards, we talked very much yesterday and today that how we are updating our design and standard and how we are going to roll out that. And then operation maintenance. Any asset that we have, we need to make sure they are in a state of good repair. So how we're going to maintain them throughout their life cycle. And part that I want to focus here is about AI. AI is hot potato. You go everywhere, they talk about AI, how they're going to use AI. I like that it was a lot of good discussion. One of the part that I think it was missing from my perspective is about the data. AI, it says artificial intelligence, but it's actually sometimes very dumb. If you give it a bad data, it gives you garbage. So one of the things that I thought it was very missing yesterday and today about the data, about the AI is data. What type of data we have that we need to put in? Even if you have a good data, but it's a biased data, you give it to AI, it gives you a biased model that is not going to work for a lot of other things. So that part of that, and why is that important? Because now we have a lot of newer technologies, drones, satellites, and other things that we can use that data to make sure that we are collecting reliable data for our models that they can produce reliable analytics. And then material and constructions, you guys are really good at that, and I don't need to talk to you about it. And the last one that was discussed actually right before this session was about governance and how we're going to do this coordination. These are some federal highway funding program. This could change because, as everyone may know, the reauthorization is going to happen this summer, and some of these programs may be impacted. With that, thank you so much, and I'll hand it back to Joe for his response.
Thank you. I'm going to stand up here. This is not on, so we're good. All right. Well, thank you for attending this session. Before we begin, just by a quick show of hands, how many people have work in architecture, engineering, or construction? Okay, so about half. What about owners and operators? Maybe a quarter. What about maintenance and or vendors of major systems? Okay, so a little bit. Okay, so mostly AEC, a fair amount of owners and operators, and a little bit of maintenance and vendors. All right, well, I always like to start with a roadmap, so this is what we'll cover during this 15 minutes. We're going to start with the overview, and we'll come back to this diagram on the right, but I want to frame it in what we'll cover with regard to two key issues. One is, at a basic level, if you take things like AI out of it altogether, imagine AI never existed as a concept. It remains the case that nowadays we have these very complex, integrated, multi-layer systems of systems that entail a lot of control systems coupled with physical assets. And I think one of the things that sets our industries apart from something like maybe like banking is there's such a direct and immediate connection between our control systems, our software systems, and physical assets. Everything is connected to something that's doing something in a real facility or on a real site for the most part. And the question becomes, as that integrated set of softwares becomes bigger and bigger, how do you design and manage a software system that might have billions of lines of code? And then second of all, when we talk about things like artificial intelligence, it's not just that AI exists, it's that primarily we use AI with people, and there's good reasons for that. So really what we're talking about are human AI robot environment teams, because that collaboration between human and AI happens in a context. So how do we manage that ethically and sustainably for the task execution that occurs within a facility? Why is this important? Before we move on to the technical stuff, I'm going to let you all read this while I talk over it just a little bit. When we perform a task, there's three things that happen cognitively, and I guess I should mention with regard to the human factors stuff I talked about at the start, my focus is more on the cognitive engineering side. So when we perform a task, let's say I move this cord around, right? There's some neurons in my brain that fire because I'm moving this cord around. If I keep doing this task over and over again, the neuron density in that area increases so that I can react more quickly and more robustly to moving that. Then what happens is because I'm generating more signals, I need more connections to support all of that extra signal, all of those extra signals that are being produced. So what happens is first when you increase your neuron density, it's called neurogenesis. When you increase your synaptic density, it's called synaptogenesis. And the cool thing is when you're using a lot more resources in a part of the brain, the next thing the body does is called angiogenesis. It increases the blood capillaries in that region to provide more glucose and oxygen. This happens all the way through your life cycle. It never stops happening. And it happens pretty rapidly. So we can't stick probes inside of humans, but they've done it with monkeys. And what you can see here is that in the case of monkeys learning to use rakes to get food instead of just using their hands, the process stabilized and was effectively complete or mature within 3 weeks. So the question is, but does it happen with humans too? And this is a correlational study with people in their 40s and 60s, generally at an age when it's considered that you're not learning as much or as well as when you were younger, and yet with as little as 40 hours of learning to play golf, of golf practice, the gray matter started to increase in specific regions of their brain. So the idea is that whenever you do anything, you don't even have to do much of it. Whenever you do anything at all, your mind, your brain, your cognition, your physiology immediately starts to reorient itself around that new task. So when you think about this in the context of the buildings we create, of the systems we use, your smartphones, your apps, the AI we're now incorporating, it's quite profound that all of these things, it's not just that we're giving people tools, we're helping them reconfigure their own physiology to support what they're doing. And this becomes a really important thing, and it gets to this topic, I think, a moment ago about AI and also where I'll end up a bit about the practical limits. So the way to understand this diagram is we have an event that's taking place. And that event entails people, it entails facilities, electricity, communications, devices, information. And there are critical perspectives onto that event and the use of those technologies and the way those people work. And these are critical perspectives that don't come from AEC, okay, or don't come from owners and operators perspectives. These are coming from systems engineering and human factors perspectives. And these are about how do you design and manage automated systems? So some of these things you may, and I would say generally speaking, where this has been advanced most, I would say aerospace and defense are decades ahead of where our industry is in terms of how do you manage the process of designing incorporation of automated systems and human automation teams into your work processes. So we'll cover some of these, but I'm going to touch on a few. Industry 3.0, 4.0, 5.0, and 6.0. So 3.0 is kind of like a building that doesn't include any advanced communication systems. You've got all your basic plumbing, electricity, telephone, basic teledata systems. Industry 4.0, you may or may not know, became a big deal about 10 years ago. It's the incorporation of IoT, connecting your communication systems. Industry 5.0, which became a big thing maybe about 3 or 4 or 5 years ago, is the realization that you can focus on all the technology, but if you don't address the human elements, the social elements, the psychological elements, many systems will still fail or at least be suboptimal. So Industry 5.0 is about looking at a human-machine system or human-machine systems. And Industry 6.0 is kind of where the industry is at, or the leading edge of the industry is, which is once you have human-machine system of systems are being tracked and monitored and measured, how do you optimize the total system of systems, everything, including your organizational dynamics? And so a lot of the rest of this stems from this pursuit, right? So a few key concepts, and one of the ways I would think about this, especially because we do have so many owners, operators, architects, engineers, and contractors, I'm sure you're all familiar with owner's project requirements and basis of design documents. It's how we start out a project. It's a great workflow, comes from the ASHRAE Guideline 0 standard. It's a great process, right? We get all of our requirements down, the owner gets them down, the operator gets them down, and then the designers respond based on what you need done, what you need to provide operationally. This is what we're going to design for you. A lot of what I'm about to cover can be incorporated into the OPR BOD dynamic to start to take into account not only the traditional MEP and teledata and whatnot of your facilities, but how do we address AI? How do we address human AI teams? How do we address heavy automation, including from a risk perspective? So key concepts. That quote at the beginning about how do you design something that takes billions of lines of code to run actually comes from a paper on what are called ultra large scale systems, ULSS, written by the Software Engineering Institute about 20 years ago. And about 20 years ago, the Army went to them and said, for a theater of war, how do we design or how do we manage a theater of war so complicated that there's hundreds of thousands of people, hundreds of thousands of assets, tens of billions of lines of code to run? And what the Software Engineering Institute came back with was this concept of an ultra-large-scale system, which is a combination of cyber-physical systems and socio-technical systems. And they basically said you can't design them, you have to grow them, you have to cultivate them. And this is key because these dynamics now are evident in the facilities we design and operate. So their point was you have cyber-physical systems, which are when you have these heavy and elaborate software control management layers, and they're all tied to physical assets or to personnel. And so it's not just about you have an abstraction like a software program, it's a software hardware system of systems, and then you have a multi-layered and diverse set of these that all have to be coordinated. But then they said, well, but the problem is you could get the cyber-physical right and the system still fails. And why does it fail? Because you did not take into account the social dynamics. And what's really interesting about socio-technical systems, there's a set of design methods that are associated with socio-technical systems, which were developed after World War II when the world was rebuilding factories after the Second World War. And they were finding that at the time, there were enough control systems integrated in these factories that they couldn't design them in the traditional way at the time. And so one of the key insights of socio-technical systems design is that because you don't know how it's going to operate, you don't know what's going to happen when you pull all the major pieces together, you purposefully, what they call under design, you get a few major components, you put them in like a pilot plant, you get some SME operators, and they immediately start working with them, and then you set up an observational study and sensors and whatnot, and you observe and you watch as they self-optimize their own processes, as they figure out how to optimize the equipment, and you track it until they get to a point where they have optimized, and then you know what the facility needs to be and do. Then you can scale up or whatnot. But the workflows associated with ULSS are incredibly relevant to our industry and something that we can participate in the design of, and mostly so that we can manage the process better than we are. Next one, levels of automation. This comes from Software Engineering, or Society of Automotive Engineers. The reason I bring it up is it's slowly, but now rapidly, being adopted by other industries. And the key thing to understand is you have this 6-point scale, and you place, so imagine your OPR BOD, and now you're going to think about your major automated systems, and you're going to try to place every one of them on this scale. So for some things you may decide, so a driver assist, for instance, those are basic rule-based systems, pretty much no conditional logic. You could think of it like cruise control. Partial automation would be like your lane keeping and following assist, where it's rule-based and there's a little bit of conditional logic, but there's not really any learning going on. Conditional automation is kind of complicated rule-based systems that may exhibit something like a little bit of adaptability, but it's still rule-based. And then where you get into automation is where you have a learning or a feedback loop. So these are things we can start to parameterize and specify, and we can borrow from best practices that have not only been developed in other industries, but that are now spreading, proliferating across industries. Next one, there's three concepts that come out of autonomous vehicle development that are also germane. Context of use, which is kind of like a big high-level description of all of the possible conditions under which your systems are going to be used. Operational design domain is like, for a given automation system that you're going to incorporate into your facility, what are the conditions under which it's expected to operate? And then operating envelope specification is, if you imagine in your facility you have multiple automated systems existing, coexisting, and some of them have to interact, it's possible that they share an operational design domain, that you have more than one automated system or human automated team in a location, and they're each performing different tasks, but their tasks are interrelated. So operating envelope specification talks, this is a NIST standard, or NIST guide document, talks about within one operational design domain, how do you specify what different human AI or automated systems are doing. Next, this was developed at technology readiness level, was initially developed by NASA around 25 years ago. It then got adopted by DoD at the time, and then other federal agencies, each one of which then modified it to suit their own needs. So, but what's happened, which is really cool, it's also proliferated, and it's also starting to show up in general industry more broadly. It's included in ANSI standards now. And in terms of the proliferation, it's grown to include integration readiness level, and then also ANSI and Human Factors in our Ergonomic Society recently wrote human readiness level. And the idea, and this gets to that socio-technical systems concept, is that you could get all the technology right, but if you're talking about systems of systems that have to be integrated, like if you assume a power plant has or a production facility or university, what have you, have multiple major systems and they all have to talk to each other. If you don't get the integration right, what happens is your commissioning phase takes years because it all gets worked out during commissioning, right? At the same time, if you don't have integrated discussion with your operators as you're developing all this, you also may end up with issues that then take years to resolve in commissioning. So somebody made the comment yesterday about this trend that they were seeing, I think it was Michael McWhorter, toward collaborative design where you have the owners, operators with the architects, engineers, and contractors all working together to scope out a facility and develop it. Everything I'm sharing with you is very much in alignment with that, but I also hope you see aerospace, defense, and other industries have actually, they're years beyond us, and there's a lot we can learn and benefit from looking at what they've done. And so this diagram is a little bit complicated. I'm wrapping up now, but I'll explain. You have here the integrated project delivery process, which is common in large capital project delivery. You have here the V model of product and systems development, which is common in systems engineering software development. And you have over here Rasmussen's abstraction hierarchy, which is common in human factors for aligning the development of systems with human cognitive ability. And what I want to show is that they're all actually incredibly complementary, as are the technology readiness level, integration readiness level, and human readiness level, so that it is possible in the span of, say, an OPR or BOD to start to incorporate all this and give your designers, not just your AEC designers, but your systems developers for your major subsystems, a guide document that lets them know where you want automation, to what degree, what kind of human automation integration is happening, as opposed to where do you have standalone systems. So to wrap it up, you start thinking about facilities we design and operate as we are cultivating them. We're not designing them and operating them. I think this would be, it helps to reframe life cycle development in those from that lens. You've got the context of use and whatnot that I covered, and two important points there. One is, one of the things that's happening with all this AI technology, you have to keep in mind that it works really well when its environment is, when the abstraction is the environment, but when the abstraction has to be tied to physical assets, it's tough, right? It struggles, and why does it struggle? Because it doesn't understand semantics and it can't independently verify anything. It doesn't have its own sensors. It can't go outside and see if the thing is sitting there or not. It's reliant upon a message in the system to tell it if it's there or not. But if the message is wrong, it doesn't know the difference, and it can't figure out the difference, right? So when you take away semantics, and then when you have limited memory, and you take away the ability to independently verify information, it has trouble with judgment. It can think of all the necessarily true things, but it has trouble figuring out which are indeed true. So along these lines, a lot of what happens is when your software developers for your major systems develop, say, a machine learning component or an AI component, a lot of times it's developed in a testbed environment, a simulation. Trouble is when you deploy it to your real facility, it doesn't work so well. And why does it not work so well? So there's an area of human factors called ecological validity, where you study the application of a system to its real environment, because ultimately you want to work in the real environment, not in the simulation. So the idea is that we have to move toward where we validate these things in an ongoing basis in an ecologically valid scenario. And then aligning with the levels of automation, TRL, IRL, HRL, and IPD, and participating in the process, and welcoming many new collaborators along the way. So I would say if the future looks much like the past, to Amir's point about data, right? If AI doesn't have judgment, and that means you're reliant on humans for judgment, then you have to let humans become experts so they can have judgment. And how do they become experts? We already covered the whole neurogenesis, synaptogenesis, and angiogenesis. Basically, if you need experts, it takes time, and you have to let them do the work to become experts. So I say the future looks a lot like the present and the past, because we still need to make experts, and the process to make experts is not different. Now, with AI, you could help use them as a study partner. There's things you can do to help maybe accelerate the trend a little bit, but not much. And then again, the key concepts that come out of this presentation, hopefully they'll be useful in you reframing how your OPRs and BODs are structured. Thank you.
Great, thank you. With that said, we're going to start off on our Q&A portion of our panel discussion. And again, if you have questions, if you wouldn't mind raising your hand, we have somebody with a microphone who will come to you. But I'm going to kick this all off with one of the questions that we discussed, but I'm going to modify it a bit. So as we're talking and integrating technologies into our systems, looking at things holistically, and talking about the good data, the bad data, and all the wonderful human intricacies that add into all of this, because, you know, us humans are just so incredibly perfect. How do we prevent AI-driven infrastructure controllers from freezing, hallucinating, or having catastrophes when we're dealing with hazards, natural hazards, or events where you wouldn't necessarily be able to simulate or test out, or, you know, you're looking at that historical data, and obviously you're just trying to implement all of these systems. There's a lot of structure, but also chaos, right? So what are your thoughts and recommendations, or do you have any?
I can start on that. So in our program, what we are looking at, we need to make sure that your systems of systems can tolerate those impacts. Just as a simple example, if I design my road perfectly, but if my bridge fails during one of these events, the network fails. If the bridge performs, the roadway fails, the network fails. If both of them work, but your slope didn't work and a slope failed, you're going to have a landslide, the system fails. So we look at how all of this is working. Where the AI helps is that, okay, how you can use some of the historical data, but with the context of predictions into the future. Just an example, when we are trying to simulate some of these extreme events, let's say flooding, the previous kind of concept was 100-year flooding, 200-year flooding, 500-year flooding. That concept doesn't make sense anymore. Why? Because just the state of North Carolina, a couple of hours south of here, they have experienced 400 or 500 flood in the past 3 years. So that concept doesn't make that much sense anymore. So how you're looking at it, you're looking at some of the what we call it scenario based, or what we call it fragility curve. So you are going to have different scenarios with different performance, and you're basically bringing your deterioration curve to fragility curve and do it. And then how you make sure that your AI doesn't hallucinate is to put safeguards. A lot of these AI tools that today we have, we think that they are really robust, but they are not. We just did an experiment in our program. We were asking different tools, Gemini, Notebook LM, ChatGPT is not very robust, or cloud. And we're asking them to give us some recommendation based on previously completed research and provide us a reference. It did that. It sounded very nice. And when you look at the reference, it made sense. They have these big names in our industry and all of that, and some of the journals. But when we went and cross-validated, half of those references did not exist. So what it did, AI brought the name of, let's say, Mr. X or someone else, put it in this journal, and create a title for that. Half of them did not exist at all. So that's what. And even when you go further and ask them to reference it, they said, okay, this page of this document, you go to that page, there are 2 words in that page that relates to the topic but does not make any sense in that context. So again, AI is good, but we need to be careful. So we need to put those safeguards. One of the things that we are doing is what we call it human feedback loop. So a lot of these ANNs, CNNs, XGBoost, random forests, these are all machine learning techniques that are really robust, or large language modeling. What we do, we put together these models or framework based on the AI, and then we bring people, SMEs like Joe and others, and tell them, we put 2 scenarios, one for AI to make a decision, one for the SME. And then we bring that SME response compared to the AI and tell to the AI, now you need to put your safeguard based on this because this is an SME response. So human feedback loop is now becoming much more mainstream for a lot of these, to make sure that we are not getting to that hallucination. So did I let Joe respond to that question too?
Yeah, thank you. What Amir says is spot on in my experience. Even though continually the technology gets better and better, the fundamental limitations I mentioned, inability to understand semantics and inability to independently verify information, these are not easier, quick things to solve. In best case, it's many years. Worst case, it's decades or more. So I would think of it maybe in terms of in the 60s when the internet was new, and I'm sure people using it at the time, ARPANET, they could envision a day when the whole world was using it and all that would be possible, but it was decades away. And the question is, how far away is this? But to going back to the point about ecological validity, this is a big part of it, is testing in as real a context as possible. And if you can't test in a real context, then if you follow the human readiness levels, the technology readiness levels, what you would find is that in those early stages, 0, 1, 2, 3, it would be perfectly acceptable to test in a simulation environment, but very quickly they're going to push you to start testing at least pieces in a real environment so that you can get a sense of if it's going to really work when you finally deploy it. The one other thing I would add is ANSI and Human Factors and Ergonomics Society are working on right now the first human AI systems testing and evaluation standards, so that you can in fact have a systematic process to evaluate does the human AI system work as well or better than just having a team of experts? So it lets you assess not only is it working, but also then you can assess whether or not it's working well enough to justify what you have to invest, and as well as the potential risk of if there's a failure or breakdown.
Great, thank you. So speaking of implementation, integration, what are some ways that human AI teams could be implemented well? And then on the other side of that, how have you seen it implemented not as well?
I try to answer the latter question first. So I think how many of people in this room, they have used ChatGPT or any of those LLMs? Okay, everyone. I challenge you to do this experiment. I have done it, and we have done it at the programmatic level. One of the dangerous things about some of these AIs are they try to make you content with what they're giving you. So they're trying to make you happy. So, and also in a very short amount of time. So next time that you're asking them a question about anything, a travel justification, or house buying recommendation or anything like that, do this. Like I've done it. Like I live in this area, so I was trying to decide, do I live in Reston or Fairfax or Alexandria? So based on the question that you give it to it, it tries to side with you always, and that's dangerous. So I was giving that question, I live in Reston, how Reston compares to the rest of this region. It gives me a list of things that, oh wow, Reston is perfect. So then next day, I said that, oh, I've looked into now Alexandria, it seems that they're really booming and all of that. How about that? And now it's trying to side with me now and say, yeah, you know, Alexandria seems that better than Reston. So the dangerous two things about some of these LLMs is that they are trying to give you an answer very quickly. If you look at like Gemini, it has 3 different modes. The first mode is a fast mode. That's the mode that you don't want to use it, especially for technical things. And the second thing is that they try to side with you. For example, if you're trying to develop a research proposal, based on the question that you give it to it, it's try to go basically get close to that rather than challenge you with something different. And that's a dangerous thing about AI. But again, like anything, we can use it in our advantage. We need just to understand those vulnerabilities. The part that I think we need to do more work about is that how to put some safeguards and how to bring, as Joe was saying, that these human experiences or human readiness level into whole discussion, not just basically relying on the AI to solve all the equations for us.
Yeah, in agreement with that, and then going back to what I mentioned, if you think about human AI team, there are 2 things you're trying to accomplish, or 3 I would say. One is we want the AI to work well. Second, we have to either develop or maintain human expertise. And the third is preferably the human AI system together is more productive, more accurate, more precise, more safe than either of them individually. So for the human using the AI system, you can imagine it as it's definitely a better search engine, right? Because you can, instead of having to try to construct your query in a very narrow way, and sometimes that's easy, but sometimes it's really hard. It's hard to get a good response. You can have more of a conversation and find your way, so that's great. But also, if you think about ways that it could help you, it can help you figure out what you don't know if you pose questions in that way and if you use proper prompt engineering. It can serve as like a study buddy, and it can quiz you or challenge you. But see, the idea is that it's helping you become an expert or maintain your expertise. It's not substituting for you. And then once you are an expert, if you're executing as an expert, you can start to automate pieces of your workflow as long as you maintain oversight. Now, with regard to oversight, and this is one of those interesting things, if you imagine like making a cup of coffee or tea, but in order to do so, you have to revalidate all of the terms. What is a spoon? What is a cup? What is tea? What is hot water? What's the right temperature? And then not only do you have to revalidate all those terms, but you have the ability within seconds to consider all possible ways you could make it. And then eventually you make your cup of tea, which is great, but how much energy and time did you just spend making that cup of energy and tea? And was it really worth it? So if you look at nature as a guide, which is what we often do, we always do, nature doesn't do that, right? If nature could have us using our gray matter to do everything, tying our shoelaces, but it doesn't, right? It automates, even within us, we automate as much of our biological processes as possible. We only use our higher intellects when absolutely necessary. Now, some jobs require more higher level cognitive processing than others, but even to that extent, so there's what's called in the human factors ergonomics world, the skills, rules, and knowledge framework. And the idea is that skills are like reflexes. It actually doesn't necessarily even go to your brain stem to process. It just, something's flying, you see something in the corner of your eye, your head ducks, your hand goes up. It takes no time at all. There's no cognitive thought at all. Rule-based is when there's skills coupled with a little bit of branching logic. So yes, no question, and then you have an automated response. So like clicking a mouse, you don't have to think about it, right? And then knowledge-based is when you're really thinking about something, what we think of as thinking. So in reality, for biological systems, as much gets pushed down to skill-based as possible, as much gets pushed down to rule-based as possible, and then knowledge-based only engage when needed. You can imagine the same is true for your organization. So, and even with regard to AI, right? We don't want everything to be open-ended. We don't want everything to be non-deterministic, a fact-finding mission. We want as much to be predictable and efficient as possible. And that means that we still defer to a lot of rule-based processes and that we use AI in very limited, focused ways. There are some exceptions to that, like if you're doing an open-ended search, but for the most part, operating facilities, designing facilities is a rule-based, skill-based process. The one other thing to add to that is, as far as human AI teaming goes, there's studies, and again, the military has done studies, it's wonderful. If it doesn't have to be AI, it can be a computer, any sort of technology. People generally assume that the technology is smarter than them. So they have studies where they'll have like a little robot that's like a scout that goes with infantrymen, and it will purposefully tell them to go into a place that's not safe. And all their training and their instincts tell them, don't go in there. But because the robot said go in there, they think it must know something I don't. They go in there and, they fail the exercise. So a lot of it too is about training your people to understand, sort of to Amir's point, this is a very powerful tool, but it's not necessarily a replacement for you and your judgment and your intuition. And so you have to use it for what it's capable of doing, but you always have to maintain oversight. But training people to do that it takes a lot of self-discipline, because it's very easy to be like, oh my God, look at what this bot just put out, and it looks really good. But to Amir's point, when you actually check it out, it's very, very shaky. And which the bad thing is, if it was shaky but easy to see that it's not valid, that would not be too bad. The trouble is, it's not valid, but it's nuanced in how it's not valid. So it actually takes a lot of work to assess.
Great.
Can I just add one more point to the follow-up of what Joe mentioned about the resources? It's very important. When we use AI, we think that, it's free, easy, and all of that. When you're generating a picture using any of these AI LLMs, the energy that you're spending on that just one task, can anyone tell me that's equivalent to how much time when you're running your microwave in your kitchen? 5 minutes, 10 minutes? Just give me numbers. 3 minutes. Any other number? 15. Any other number? 1 hour. Any other number? Plus 100 hours. If you run your microwave 100, actually it's getting close to thousands. For 100 hours non-stop, that's equivalent to just generating one picture. So it goes back to the resources, because we think these are free, these are not free, these are resources that you are spending to get answers that is also shaky, that you need to spend your human basically resources to verify them. Again, don't get me wrong, we use AI every day and it's powerful. We need to understand its vulnerability and also its advantages and disadvantages to use that efficiently. Right now, what I see that sometimes we use AI it's becoming a wild west, to be honest with you guys. So that's just to put some kind of cautionary about how we are utilizing some of these tools.
And to add to that, that's why you might use something like the levels of automation scale in your OPR, BOD to think about where do we really need this technology, and you assign per operation what's going to have that level of automation or the ability, to bring intelligence and learning to a system versus not. Because again, in nature, the vast majority of systems, they use that level of processing to the minimum extent possible, and they create rules and skills. And mostly that's how our facilities run, right? Everything is rule-based and skill-based. From an energy use and information processing load and time to process perspective, it's likely that in the future that remains true. So the question is, where do you benefit most from the application of an advanced, system that can learn and do it, function as an AI functions?
Any questions? If not, I have one additional. Okay, great. Microphone, yeah.
It's a little bit of a can of worms, but I want to dive into digital twins if you guys would be willing. So I've seen digital twins that are amazing inventories. A building with every nut in the building is accounted for, and it really helps with maintenance and design and everything like that, operations and maintenance. And we also, video games, can basically create simulations that are practical reality. And we have great tools for risk assessment, data analysis, curves, statistical packages, everything like that. But what I haven't found, except occasionally, is a digital twin that integrates all of that so that they can do human digital analytics and sort of help you chart your own adventure using the digital twin and then getting numerical feedback as you go. Have you guys run into that?
Yes.
Okay.
Great. And if you want to talk more, so again, going to the idea that other industries are ahead of us, you may have heard of CATIA, which Frank Gehry used to design Bilbao and others, and he was deploying software mostly used to design aircraft, to design buildings. Well, the company that makes CATIA, Dassault Systems, and Siemens and some other companies have packages and tools that do this. They're just not traditionally used in our industries. But I can share with you.
Great, thanks.
There's a gentleman behind you that has his hand up.
Thank you for your presentations. Joe, just had a question. Could you elaborate a little bit more on the note you said that we cultivate facilities, we no longer design facilities? I'm an architect, so I'm intrigued by that statement.
Yeah, sure. So if you think of participatory design is what we've traditionally called it. But participatory design for us is really, we get all the stakeholders together early on and we're talking to them about traditional things that architects would be concerned with. And it's like an option, right? It's not something you have to do. It's maybe a nice to have. I think the shift that I expect is that we'll find that participatory design is not a nice to have or an option. It's the way things get developed, period. And that if you don't have the stakeholders participating, the implications for cost and operational use are significant. Basically, so what I would expect to see is a transition to where that becomes the norm.
It kind of goes totally against the grain of how I was, and others I'm sure were educated. I can give an example. Stanley Tigerman was the lead architect at University of Illinois Chicago, and I was giving a presentation. I was, I think, my sophomore year, and I was describing how my building was designed and why I did what I did. And I had made the comment, they asked, why did you put the front door there? And I said, well, based on how I felt the pathway, you know, through the building and so forth. And I also then added, well, also working with the owner, if there was needs that they were interested in, based on where I located, I worked with them to develop that plan. And he got totally upset with me that, you know, you are the architect. You are setting the goal and the reason for what you're doing, and the owner should have no input. And, you know, that was 1986.
Yeah, that's
you know, it's just, it still blows my mind today, you know, that this idea of a star architect, you know, has this prominence that there should be no interaction and a participatory type of cultivation of ideas.
Yeah, it still exists. I think there's a great paper by Rasmussen who came up with the abstraction hierarchy about how he traces from the turn of the 20th century, so around 1900, where you have the very first control systems showing up in factories. And at the time series studies, you know, became a tool to use to understand how master craftsmen performed a task, so that then you could teach others how to do it the same way. And he traces how somewhere in the post-war era, 50s or 60s, was the first time, he said, until the 50s or 60s, you could start, you know, when you were, let's say, a teen in a facility, and you could become a master, so that by the time you had 20 or 30 years there, you truly knew how everything worked. You could fix everything. You could direct others to fix everything, but how in the post-war period was when control systems and systems, even physical systems, first got so complicated that nobody could ever become a master. It was just not possible. And then he traces it through to the 80s, which is when he was writing this, and how then you have automation and computing becoming a thing. And his point was, how does somebody design or operate a facility that nobody can ever understand? Nobody will ever be an expert in it. And so that's where a lot of these methods, socio-technical systems, some of the stuff I showed, they've been developed over time in other industries to try to manage the risk and parameterize or put bound the system complexity, put bounds on systems that have to be designed and operated that nobody will ever fully understand. And that, what you mentioned, is a pernicious thing, right? That whole idea that you could have this sole genius expert who knows everything, it's unfortunate that it persists.
Great, thank you very much. And thank you all for attending. Thank you, Joe and Amir. Very much appreciate your presentations and the great discussion. If you guys would like to have any questions, Amir and Joe are going to be here throughout this afternoon. And we are now into a break until 11:15, which is when the next set of breakout sessions will start. Thank you.